Explosions. Powerful, sudden, and often devastating. But, what exactly is an explosion? What causes them? Are all explosions the same? And how can we scientifically classify them? This video kicks off a multi-part series with an introductory approach, where I invite you to dive with me into the science of explosions, from their causes and characteristics to the chemistry of the materials behind them. Whether you're here for curiosity, research, or engineering insight, you're in the right place. The Science of Explosions. A series of videos. Part 1. An Introduction to Explosions. At its core, an explosion is a rapid release of energy, usually accompanied by heat, light, sound, and a shock wave. This energy comes from different sources: chemical reactions, physical ruptures, electrical faults, or even nuclear reactions. What all explosions share is their ability to release energy so fast that it causes pressure waves and potentially destruction. The key feature of an explosion is the creation of a pressure wave, a sudden increase in pressure that moves outward from the source. This can be strong enough to break structures, project debris, or cause serious injuries. The violence of an explosion often depends on how fast the energy is released and how confined the reacting materials are. For example, a firecracker releases energy quickly, creating a loud bang and flash. But a ruptured gas boiler can create a shock wave capable of demolishing walls. Same principle, different scale and materials. Let's start with how explosions are categorized based on their energy source. They can be categorized as chemical, nuclear, mechanical, electrical, and thermal. Chemical explosions. These are the most common categories. They result from exothermic chemical reactions, typically involving rapid oxidation. These can be caused by high explosives, like TNT or RDX, which detonate and produce supersonic shock waves. These are used in demolition, military munitions, and mining. Low explosives, such as black powder, which burn rapidly deflagrating, but don't detonate. They are used in firearms and fireworks. And fuel-air mixtures, where dispersed flammable gases or vapors ignite in air, such as a gas leak igniting in a kitchen or industrial site. These can be highly destructive if the vapor is well mixed with air before ignition. Nuclear explosions. They occur when energy is released from atomic nuclei via fission or fusion, producing immense heat and shock waves. The detonation of an atomic bomb is a classic example, unmatched in energy release and consequences. Mechanical explosions. They occur when a pressurized system, like a gas tank or boiler, ruptures violently. No chemical reaction is required. A classic example: an overheated gas tank that bursts due to internal pressure buildup. In 2010, a water heater at a factory in Connecticut exploded due to a pressure buildup caused by a failed relief valve. The blast tore through walls and caused several injuries, highlighting how unchecked pressure alone can generate destructive force. Electrical explosions happen during arc faults or electrical breakdowns that vaporize conductors, or ignite surrounding materials or explosive atmospheres in industrial environments. In 2008, A large-scale arc flash explosion occurred at a power plant in Arizona when an electrician opened a panel energized at 13.8 kV. The resulting arc created a powerful plasma burst, injuring workers and severely damaging equipment. And last but no least, thermal explosions are caused by uncontrolled heat buildup, often in chemical processes or poorly ventilated spaces. For example, when reactive chemicals accumulate heat faster than it can dissipate, pressure builds until the system fails catastrophically. In 2007, a warehouse in Ghent, Belgium, exploded after heat buildup in containers of organic peroxide caused a thermal runaway reaction. No fire was initially involved, just poor ventilation and reactive storage. The speed of the reaction matters. Explosions can be also categorized by how fast the reaction spreads. This includes two types of phenomena: deflagration and detonation. Deflagration is a subsonic combustion wave, like the burn in fireworks or a fuel air flash fire. The flame front moves through the material by heat transfer, characterized by conduction and convection. It's typical in low explosives like gunpowder, and in some accidental fires. A grain silo dust fire can deflagrate and still cause serious damage. Detonation, on the other hand, is a supersonic shock wave driven by the chemical reaction itself. This is what happens in high explosives and some fuel-air bombs, where an instantaneous, massive energy release takes place. It compresses and heats the material ahead, sustaining the reaction front. High explosives like PETN or C4 detonate, releasing tremendous energy almost instantly. The 1917 Halifax explosion, caused by a ship carrying high explosives, is a tragic historical example of detonation on a massive scale. Some explosions occur when a combustible material, solid or liquid, is dispersed in air, creating a highly reactive fuel-air mixture. These are called dispersed phase explosions and include dust, vapor cloud, boiling liquid expanding vapor, and thermobaric explosions. Dust explosions. When fine powders like flour, sugar, coal, or metal dust become airborne and ignite, deflagrating violently, with results that can be devastating. The 2008 Imperial Sugar Refinery explosion in Georgia is a well-known case. Vapor cloud explosions, also known as VCE, happen when flammable vapors, like propane or gasoline, leak and form a cloud. If ignited, the result can be devastating, especially in industrial settings. This was the mechanism behind the 2005 Buncefield Oil Depot explosion in the UK. Boiling liquid expanding vapor explosion, also known as BLEV, happens when a pressurized liquid overheats and its container fails. The liquid vaporizes explosively, often followed by a fireball. In 1984, a massive BLEV occurred in San Juanico, Mexico, when a series of propane storage tanks overheated and exploded. The resulting fireballs and shockwaves killed hundreds and caused widespread devastation. Thermobaric explosions. These are engineered fuel-air mixtures designed for maximum overpressure and heat. Used primarily in military applications, they produce a longer-lasting shock wave and a powerful blast by using atmospheric oxygen, increasing destructive potential inside enclosed spaces. In 2002, during the conflict in Afghanistan, the U.S. military deployed thermobaric weapons in cave systems. Their ability to produce extended, high-temperature shock waves made them particularly effective in enclosed or fortified positions. Understanding explosions is about more than curiosity. It's critical for preventing industrial accidents, designing safe infrastructure, investigating crimes and incidents, developing better tools for rescue, defense, and space propulsion. This knowledge sits at the intersection of chemistry, physics, and engineering, and affects everything from workplace safety to national security. This is just the beginning and the surface. In the next videos, we'll explore each explosion type in depth, starting with reaction mechanisms, then diving into flame propagation, dispersed fuel-air systems, and eventually the chemistry of energetic materials and the true power behind detonations. If you could ask a forensic chemist or blast expert one question about explosions, what would it be? Leave it in the comments and I'll try to include it in the series. Subscribe and follow the series to explore the science behind explosions and how we can harness or prevent them. Thanks for watching.